Okay, so here's our unit circle that we've been talking about, and it looks pretty empty, it looks pretty blank. That's because this is for us to fill in, and this is how we are going to get familiar with that unit circle. So here's a circle, and just trust me, it doesn't look like it's a radius of 1, but 1 unit can be any size. So this is a radius of 1, and so we call this the unit circle. And what we want to do is look for the exact values along this circle and all of its multiples. So we're going to start off by doing what we did in the warm-up and basically filling in our multiples of 30 and 45. So let's take a look at the circle and see if we can split this into quarters. So we've got each quadrant that we're going to split in half. So that's a 45 right there. Of course, the 90. And then we split the second quadrant in half. So you see we split this half circle, the top half. So looking at that top half of the circle, I've split it up into fourths now if you think about the axes, also dividing the circle. And so then there's, of course, the 45s down at the bottom here. So you've got one there. And then, of course, one splitting up the fourth quadrant. And speaking of the quadrants, I think we maybe better establish the quadrants before I assume that you know them. So the quadrant that we're both of the x and y coordinates, when we think about the coordinate plane, we think of x and y's, right? And we know that they're both positive in the first quadrant. So this would be the first quadrant. This would be quadrant 1. And then we go counterclockwise around. We call this quadrant 2. We call this one down here quadrant 3. That's where both x and y are negative. And we call this one quadrant 4. So if we fill in these multiples of 45 degrees, there's 45 degrees, and there's a place here to put the degrees in the center. So there's 45 degrees, and then of course there was the 90 degrees, so we can go ahead and fill that one in now. Then there's another 45 degrees, makes us to 135. And then the next one would be at the 180. And then the next multiple of 45 is 225, so that would be right here. And then the 270, that's another 45 degrees. And then from there, that's 315. And then finally up to 360, which is also the same as saying 0 degrees. So actually, I think they wanted us to put that underneath 360. And then we could put the 0 degrees on the top. And now the multiples of the 30 degrees. So let's see, the first one would be, of course, 30 degrees. And then the next one would be 60. And then the next one's 90, but that one's already labeled. And then the next one would be 120 degrees. And then 150, 180, which would be 30 times 6. Then 30 times 7, that's 210. Then 30 times 8, that's 240. Then 270. Then another 30 is 300. One more is 330. And then, of course, we're back up to 360. So we have all the multiples of 30 and 45 degrees. And we talked about these special angles in the sines and the cosines and the tangents of these degrees, the 30, 45, and the 60 degrees. And we used this little hand trick. Now, at the time we learned this finger trick, we didn't actually know this fact. And the fact is that the cosine is like the x coordinate in the unit circle. So when we talk about finding the cosine, it's like finding the x coordinate of a point on the coordinate plane. So in other words, like if I were to, say, take the point here that's at 30 degrees, and I wanted to find the cosine, it would be the same as the x coordinate. And the sine would be the same as the y coordinate. And so when we were actually using our finger trick, we always said that the cosine was the number of fingers. When we bent down our finger that represented that angle measure, it was the number of the square root of the number of fingers to the left, and that's because when we think about our ordered pairs, the x coordinate is the left coordinate, and the y coordinate is the right coordinate. So the sine is associated with the y, and the x is associated with the cosine. So we use this special finger trick to help us remember these special angle measures and their trig ratios. So taking a look at the 45s, remember that the sine and the cosine of 45 were the same, and that's because if we thought about lowering our middle finger, which is associated with the 45-degree angle, that means we have two fingers to the left and two fingers to the right, so the square root of 2 over 2 would be the sine and the cosine of 45 degrees. And the tangent, which we talked about, compared the sine to the cosine, or the number of fingers to the left, square root of that divided by the number of the square root of the number of fingers to the right, and so since they were the same, they canceled each other out, gave us 1. The tangent was 1. So if we went and looked on this unit circle to where 45 degrees is, which is right here, this one right, let me circle it, here, when we talk about the cosine, we're saying the x-coordinate, in other words, the number of units from the origin, we'd have to move to the right to get to this point, and that would be the square root of 2 over 2, and then the number of degrees units we'd have to go up, which is also the square root of 2 over 2. And you can kind of think about if we were to draw in the rest of that and make a triangle here with the x-axis, you can see that it looks like it's an isosceles right triangle. And in fact it is, because this measure right here is the square root of 2 over 2 units, and this right here is the square root of 2 over 2 units. So the x and the y coordinate are associated with the cosine and the sine. So what about the 30 degrees? Okay, so let's look at the sine, cosine, and tangent of 30. So 30 degrees is this finger right here. We're folding it down. We're thinking about how many fingers are to the left. We're taking the square root of it and dividing it by 2, and that means that that's the cosine. So the cosine, which is to the left, will be the square root of 3 over 2. And the sine will be the square root of 1 over 2, and the square root of 1 is 1, so that's 1/2. Now when we think about the tangent, that's the sine over the cosine, so the sine would be the number of fingers to the right, so that's the 1, so we have the square root of 1 over the square root of 3, which then means 1 over the square root of 3, and of course we can rationalize that, and that gives us our tangent of square root of 3 over 3. So that one's not as easy to do, the tangent isn't, but it's definitely doable as long as we remember that the tangent is equal to the sine over the cosine. So now if we come over to our circle and we actually put those on our graph, when we locate that point at 30 degrees, then the x-coordinate will be my cosine, and that was the square root of 3 over 2, which by the way as a decimal is about 0.866. And then the sine was 1/2. And so it's like we're saying, okay, well, we've got to go this many units, so to the right from the origin, and this many units straight up on a right triangle, to get to that. And it's like saying this one right here, this dimension, which is the y, is 1/2, and this dimension right here, which is the x, is the square root of 3 over 2. So that certainly makes sense because that is longer, the square root of 3 over 2. That's just short of 1. It's 0.866, so it almost got to the 1, and then it had to go up 1/2. So that's where what those coordinates really mean is the location on the circle, the coordinates that would locate that point on the circle. Okay, so now the 60 degrees. So the 60 degrees, cover up that finger, and we've got one finger to the left, and that's associated with the cosine, so it's the square root of 1 over 2, and that's really 1/2. So that's 1/2 for the cosine. That leaves the square root of 3 over 2 for the sine. And that means the tangent is going to be the number of fingers on the right, which is that you have the square root of 3. And then on the bottom, the square root of 1. And so we know that the square root of 3 divided by the square root of 1 is really just the square root of 3. So that's the tangent. And now I go to my circle and I locate that 60 degrees, and here it is right here, and I can fill those in, so I know that my cosine is 1/2 and my sine is the square root of 3 over 2. I should probably write the tangent of 30 also on here. So the tangent of 60 degrees was the square root of 3, and the tangent of the 30 degrees was the square root of 3 over 3. And again, you can make that association with the triangle, and at 60 degrees this would be the triangle that would be made with the origin, and you can see that to go to the right, your x-coordinate, you have to go about 1/2, and then you'd have to go up, it looks like, just below 1 unit, and so that's that square root of 3 over 2. So those coordinates are the locations of each of these segments that connects to the origin, so they're associated with the angle measures. They're the x and y coordinate that locate them on the unit circle. Let's actually let's finish, because we know that idea about the x and the y coordinate. Then we can actually finish this the first quadrant and the axes. We could look at 0 degrees. So to get to this point at 0 degrees right here, we would just simply have to go 1 unit to the right, which means the x coordinate is 1, and no units up, which is 0. And what that really means is that means that the cosine of 0 degrees is 1, and the sine of 0 degrees is 0. And so if we took the tangent, and if we know that the tangent is the sine or the cosine, well, the sine is 0, the cosine is 1, 0 divided by 1 is 0. So the tangent of 0 degrees is 0. And if we went up here at the 90 degrees at the top here, we could do the exact same thing, and we could locate that point, and we don't go left or right at all, so the x-coordinate would be 0, which means the cosine is 0, and we have to go up 1, so that makes the sine 1, and so we could say that the cosine of 90 degrees equals 0, the sine of 90 degrees equals 1. And then if we think about the tangent is the sine over the cosine. So if we divided the sine, which is 1, by the cosine, which is 0, we'd actually get undefined. So the tangent is said to be undefined. So that gives us the first 90 degrees. So what about the rest of the circle? Well, because we know that all the rest of these angles are actually multiples of 30 and 45 degrees, and even of 60 degrees, we actually know that their sines and their cosines and their tangents will be basically, I guess if you think about the absolute value, the same as the ones in the first quadrant. But remember, as you move to different quadrants, the x and the y's sometimes are positives and sometimes are negatives. And so instead of, say, for instance, if I looked at the angle that was at the same number of degrees up from the x-axis, but in the second quadrant, so instead of going up 30 degrees this way, if I went up 30 degrees this way, that 150 degrees is, which doesn't really look like it's, maybe because I went out a little too far, that is the reference angle. It's the same position, but instead of going to the right and going up as we did to get to 30 degrees, we had to go to the left, which means negative, and go up. And so we can just use the same values that we used for 30 degrees, except for we'll have to adjust for the fact that we had to go left so that our x-coordinate, or our cosine, is negative. So 150 degrees would have a cosine of negative square root of 3 over 2 and positive 1/2, because we're still going up for the sine, or the y-coordinate. And it actually turns out that every one of these special angle measures in the second quadrant will have a negative cosine, and it will have a positive sine. And so if you look at the 135 degrees, that's a multiple of 45 degrees. So it's kind of like saying, this is like your reference angle. So instead of going up 45 degrees this way, we're going to go up 45 degrees from the x-axis on the other side. So the thing that's going to change, you're still going to have the same coordinates, but your x-coordinate will be negative. So we'll have negative square root of 2 over 2, and the sine will be square root of 2 over 2. And then for 120 degrees, you can think about, get a different color here, blue, and if we rotate up to 60 degrees, this is how far we have to go. Well, going that same on the other side would take you to the 120 degrees, and so we know that it will have the same x and y coordinates, but the y will be positive and the x will be negative, so it'll be a negative 1/2 for the cosine and a positive square root of 3 over 2 for the y. So basically these points are reflections of a point in the first quadrant. 150 degrees is the reflection of 30 degrees. 45 degrees, if you reflect it over, you get 135. You reflect 60 over, you get 120 degrees. And so we can get these trig ratios just by knowing the ones in the first quadrant. And this is exactly why we talked about reference angles in the last lesson, because we can use reference angles and just adjust the sign, and I don't mean the SIN, but the SIGN, positive or negative sign, based on where we are in the quadrants. And so there's another really easy way, another little trick, I guess, like besides the hand trick, that you can use to help you figure out what things, sine, cosine, and we haven't talked about the tangent yet, that will be positive in whatever quadrant you're in. So this is kind of a little, just like a little trick that helps you remember that. So I just created a little quadrant, a little coordinate plane here, and so I've got my 4 quadrants. So of course this is the first quadrant, second, third, and the fourth. And I think that awesome students take calculus. Now that's not my selling tip to try to get you to take calculus, but it actually is a way of helping you remember what of the 3 main trig functions is positive depending on which quadrant you're in. So if you start in the first quadrant, I use the word awesome, which starts with an A, and that really means all. Everything, sine, cosine, tangent, will all be positive in the first quadrant. In the second quadrant, students, well, sine starts with an S, and only the sine is positive in the second quadrant, because remember the tangent is the ratio between the sine and the cosine, so if the cosine is negative there, then you divide a positive by a negative, you get a negative. And then takes starts with a T, and so does the tangent. So the tangent is the only one that's positive here, and that's because if you're dividing the sine by the cosine to get the tangent, you're dividing 2 negatives, and so 2 negatives divide to give you a positive. And finally, in the fourth quadrant, C, calculus. Well, calculus starts with a C, and so does cosine. So in this quadrant, only the cosine is positive. So if you think about that, awesome students take calculus, and going around through the quadrants, it'll help you to remember when you're in that quadrant how you're going to have to adjust the SIGNs, the signs, positives and negatives of these special angle multiples. So since I said students was in the second quadrant, only sine is positive, so far we see all the sines written, but we haven't written the tangents. So the tangents are also going to be negative. So the tangent of 150 degrees is going to be the same as the tangent of 30 degrees, so it's going to be the square root of 3 over 3, but it's going to have to be negative. So that's the tangent of that angle, 150. The one for 135 is the same as the one for 45, but it's got to be a negative, so it is -1. And then that's going to leave the tangent of 120 degrees to be negative square root of 3. And what about 180 degrees? Well, 180 degrees is at the position that's the reflection of the 0 degrees. So that means that the cosine will have to be -1, because that's the x coordinate, and the sine would have to be 0, because you don't go up at all to get to that point. And then, so if we look at the tangent of 180 degrees is actually going to be the sine, which is 0, over the cosine, which is -1, and so that's still 0. This tangent is still 0 over there because that's actually on the axis. And now this process can be continued throughout the whole rest of this unit circle, but just by thinking about reference angles. So, we know that 210 is a reference angle with the 30 degrees because it's 30 degrees away from the x-axis. And so we can use the same measures for 30 as we do for, we can for 210 that we use for 30. So that means square root of 3 over 2 for the cosine and a half for the sine. But this time they're both going to be negative because we're in that third quadrant. And that means the tangent is going to be, if you divide a negative by a negative, you get a positive. So the tangent is actually going to be a positive square root of 3 over 3. When we go to the 225, we're going to still use the same cosine and sine. They're the square root of 2 over 2, but make them both negative this time. And then the tangent is going to be a positive, but it's going to be a positive 1. And finally, in this quadrant, we have the 240 degrees. It's going to be the same as the 60 degree values. So that means it's going to have a cosine of a half, but negative, and a sine that's the square root of 3 over 2. And then the tangent is going to be a positive value, but it's going to be a positive square root of 3. Well, what about 270 degrees? Well, 270 degrees, to get to that point from the origin, we just have to go down 1, but not left or right at all. So the x, or the cosine, is 0, and the sine is -1. And so that means, so this is our cosine is first and then sine, so that means our tangent is going to be equal to the sine, which is -1 divided by 0. So again, that is, you can't divide by 0, that's undefined again, just like the one at 90 degrees above it, because it's the reflection over the x-axis. So we're almost done with the unit circle, and it's getting kind of busy. But I want us to have you pause the video now, and I want you to try to fill in the fourth quadrant, keeping in mind that awesome students take calculus, so the cosine is the only one that's positive here. So fill in the rest of this unit circle, and then tune back in to make sure you got the right values. All right, so go ahead and check them out and make sure that you have the correct signs as well. The signs, S-I-G-N's, on the sine, S-I-N, should all be negatives. Cosine should be positives, tan should be negatives. Because awesome students take calculus, cosine's the only one positive here in this fourth quadrant. Well, this is getting kind of busy, and I hope that because your page is a little bigger than mine to write on, because I'm writing on my iPad, that you've had space to fill all this in. But there is one more line on this circle, and you're probably wondering why we haven't filled that in, or maybe you were thinking that's where we were supposed to put the tangent. But we actually left room on the unit circle for the radian equivalents. So we've been talking about radians and how you convert them. Well, there's actually a really easy way to find the related radian measurements for these special angles as well. And you can do this by just splitting the unit circle into multiples of pi over 4 and pi over 6. So remember we talked about that we could find the 45s, the multiples of the 45, by splitting the half circle above the x-axis into fourths. So basically we were splitting the whole circle into eighths. But if we think about that 45 degrees is pi over 4, then we can kind of get multiples of pi over 4. And why pi over 4 is this. if you think about traveling along the circle till you get to 45 degrees, you've actually gone a fourth of the way around to 180 degrees. And so I actually know that 45 degrees is pi over 4 radians. And then if I went another, so that's 1 pi over 4. So 2 pi's over 4 would take me to 90 degrees. And 2/4 reduces to a half. So that's 1/2 pi, or pi over 2. So then that was 2/4. Now 3/4 would be the next one. So this is 3 pi over 4, or 3/4 pi. And then the next one would be 4/4, which 4/4 is 1, so that's just pi. So this one is pi radians. So then we go another fourth. So we were at 4/4, so 5/4. So the next one would be 5/4. That's at the 225. 5/4 pi. The next one would be 6/4, which is 6/4 is reduces to 3/2. So that's 3 pi over 2. And remember, 3 halves is like 1.5. So it's like we've gone 1.5 times pi, because pi is, halfway around. So we've gone 1.5. So the next one would be 7 pi over 4, which doesn't reduce. Oops, I wrote it on the wrong spot. And then finally, we would get back to 0, and that would be 8 pi over 4, which is 2 pi. So that makes sense. So the 30-degree multiples are going to be multiples of pi over 6. So 30 degrees would be pi over 6, which makes sense because if you've gone 30 degrees here, you've gone a sixth of the way to 180 degrees. So that's pi over 6. Now another pi over 6 would make 2 pi over 6. So we have 1 pi over 6, then 2 pi over 6, but 2/6 reduces to 1/3, so that's really pi over 3, or 1/3 pi. Okay. Then the next one would be 3/6 pi, which 3/6 is 1/2, and that puts us right back at 90 degrees again. Then the next one would be 4/6 pi. Well, 4/6 reduces to 2/3, so that's 2/3 pi, or 2 pi over 3. The next one would be 5/6 pi, so that one doesn't reduce, so that's 5 pi over 6. Then 6 pi over 6, of course, would be, 6 divided by 6 is 1, so that's pi. Then we have 7 pi over 6 for the next one. Then the next multiple would be 8 pi over 6, and 8/6 reduces to 4/3, so that's 4/3 pi. Then 9/6 pi, so then 9/6 reduces to 3/2. We're down there at the same spot as 3 pi over 2. And then the next one would be 10/6. So 10/6 pi would reduce to 5 pi over 3, or 5/3 pi. And then 11/6 pi, or 11 pi over 6. And then 12/6 pi, which is, again, 2 pi. So the 30-degree multiples are all multiples of pi over 6. And all the 45s are all multiples of pi over 4. And they're all just reduced. So some don't look like they're all multiples of pi over 4 because we reduced, or pi over multiples of pi over 6 because we reduced. That is a lot to put on one page. I think that might be the record for me. So I think it's time that we start a new page. So let's move on to the next page. Okay, so let's say we wanted to use the unit circle to find the exact values of each trigonometric function, but we couldn't technically use the unit circle. Like, for instance, it's not allowed, maybe allowed on the test or something. So let's say we wanted to find the cosine of 225 degrees. Well, if you think about 225 is one of those multiples of 45. As 45 goes into 225 5 times. And so when I think about where that's located in the coordinate plane, I usually like to draw a picture of it. And I think about 225 degrees, I'd have to go 180, and then I'd have to go 45 more degrees. So I would end up right here in the third quadrant. And so I think about awesome students take calculus, because remember, awesome students take calculus. So first of all, I know that this is going to have as a reference angle 45 degrees. So I know it's going to have a cosine that's square root of 2 over 2 without considering the sine, but I'm in the third quadrant, where just the tangent's positive. So that means my cosine has to be negative square root of 2 over 2. So basically what we're doing is we're seeing what of those key values, 30, 45, or 60, is this a multiple of? And then we're taking whatever the cosine or the sine or the tangent is from the first quadrant and then just adjusting it to make it positive or negative based on where it's located in the coordinate plane. Okay, so what about the tangent of 5 pi over 6? Oh, well, that's a little harder when it's radians. But you think about 5 pi over 6. So that means we're only a sixth of the way. If you think about that, we're only a sixth of the way from pi because we're 5/6. So that means we're only 1/6 of the way away from the x-axis. So our reference angle must be 30 degrees. And so we think about the tangent. Well, rather than memorizing the tangent, you might just remember that it's this. You can think about it as the sine over the cosine, and we can even think about it as the sine of 30 over the cosine of 30, but then we just remember we have to adjust it because in that quadrant the tangent's going to be negative. And so we just know we could take the sine of 30 and the cosine of 30, or we could even use our finger trick, and we could think about putting down our 30 finger, which is our pointer finger, and that means our sine, we have the one finger, which is our thumb, to the right, and that's the square root of 1, and on the other side the 3, so it's the square root of 3. Well, that means 1 over the square root of 3, that means it's the square root of 3 over 3, and finally we have to make it negative, because in that quadrant the tangent is negative. Okay, so 315 degrees is, I went all the way past 270, and then to get 315 I have to go 45 degrees further, so my reference angle must be 45 degrees. So I'm going to get the values for 45 degrees, but then I'm going to have to adjust it because I know that awesome students take calculus, so sometimes it helps to write that awesome students take calculus. And so I know only the cosine is going to be positive in that quadrant, so I'm going to have a negative value, and then the sine and the cosine of the reference angle 45 degrees are the square root of 2 over 2. So this must be negative square root of 2 over 2. The tangent of 180 degrees, well, remember 180 degrees is right on the x-axis, and its coordinates there at 180 degrees are -1 and 0. So if we think of it as the sine over the cosine, we know it's 0 over -1, which is 0. So the tangent is 0. And what about 4/3 pi? So we think about 3/3 pi would be if we went a full pi. So if we went another third beyond that, so a third of the way around, would actually put us at a reference angle of 60 degrees. So if we use the reference angle of 60 degrees, but you know it's the cosine, so awesome students take calculus, awesome students take calculus, I know that that means the cosine in this quadrant, which is the third quadrant, is going to be negative, and I'm going to use the same cosine as the 60 degrees. So if I think about holding down my ring finger, which is my 60-degree angle, and I hold it down, and I know that my cosine is to the left. So I have one finger to my left of my ring finger, and so it's the square root of 1 over 2, and the square root of 1 is 1, so that's really just -1/2. So the key is really just being able to figure out these reference angles, and then if you've committed those to memory or used the hand trick or whatever, and adjusting for the quadrants and the SIGNs in them, then you know this actually is a really easy task to master. And this box over here, this really is just sort of a recap of what I talked about with awesome students take calculus. There was a place for you to kind of indicate which things are positive, but if you use the awesome students take calculus, this is easy to fill in. That's in the first quadrant, all of them are positive, everything's positive. In the second quadrant, only the sine's positive, everything else is negative. In the third quadrant, only the tangent's positive, the others are negative. And in the fourth quadrant, only the cosine is positive, the others are negative. So this is another way to remember it. But I really think that awesome students take calculus has been the easiest way I've seen students learn that. Okay, so example 3 asks us to use reference angles to evaluate trig functions, which is really what we've just been doing here. And because at each one of these questions they want you to find the sine, the cosine, and the tangent, and there's actually 4 of these, there's a few more on the next page, we're going to leave these to be in-class you-try questions because we still have one more learning goal to get to. So we're going to go ahead and just leave this example A, and then if you turn the page, the next 3 on this page, and we'll do these to start our next class together. And that way we can kind of test for understanding. Let's see if there's anything that we're still struggling on by doing those examples in class. And so we're going to go ahead and move on and look at this last example about finding arc length. So arc length, that might sound familiar to you. We actually learned how to calculate arc length in geometry, and this was actually the formula that we used. So the arc length formula works like this. You find the length of an arc, which by the way we designate sort of like we're writing it as a segment, but we use a little curved arc above it, remember that? And basically the arc is a part of a circle. So in this case, the one that's highlighted here in yellow, labeled as S, that would, if I wanted to know the length of that arc, what I'm actually asking for is a part of the circumference. Because all the way around the circle would be called the circumference, and so I'm only going part way around. Well, it turns out that this formula adjusts for that fact that we're only doing a part of the circumference. This part right here, the 2 pi r, remember that's the circumference formula. And the other part right here actually represents what fraction that little slice is out of the circle, and where m stands for the number of degrees of the central angle. So if we knew the angle, say if we knew like the measure of this little angle in here, we would call that m in degrees, and we would divide it by 360 because then that told us what fraction of the whole circle we had rotated through. And then we just multiplied by the circumference. Well, the problem here is that we're not always given the central angle as a degree measure. Sometimes we're given an angle measured in radians. And so we have a need for a different formula, a formula that takes into account that angles are measured in radians instead. And that's what this formula is. So this formula says for a circle of radius r, so r stands for the radius, the arc length s, so we use S for arc length, intercepted by a central angle of theta measured in radians, that was important, it's measured in radians, is given by the following formula. It seems like a pretty simple formula. S equals r times theta. In other words, you can find the arc length by simply multiplying the radius of the circle by the angle measured in radians. And so I always refer to it as radius times radians, because that's what I have to do here. I have to find out theta in radians, and I have to multiply that by the radius. So arc length equals radius times radians. Let's take a look at an example that involves an automobile application. So a tire of a car makes 653 complete rotations. So I'm going to just kind of circle stuff that's important or highlighted or whatever. So 653 complete rotations in 1 minute. That means in 1 minute it's going to go completely around the whole circle 653 times. The diameter of the tire, so they're giving me the diameter of the tire to be 0.65 meters. To the nearest meter, how far does the car travel in 1 second? Okay, so we want to find out how far, which means a length, the distance that it's going to travel in 1 second. So here are the steps we're going to have to take to actually answer this question. The first thing is we have to find the radius of the tire. Well, they gave us the diameter, so I know that radius is equal to the diameter divided by 2. So the diameter is 0.65 meters, and I'm going to divide that by 2 to get 0.325 meters. First of all, I'm going to find, for step 2, it says find the angle through which the tire rotates in 1 second. But actually the measurement that I'm given is for a minute. So I know that this tire travels 653 complete rotations. Well, that means it rotates around an entire circle 653 times. Well, remember, an entire circle is 2 pi radians. All the way around is 2 pi, right? And it does that over a span of 1 minute or 60 seconds. So since I want it in seconds, I'm going to change 1 minute to 60 seconds. So now all I have to do is find out what this turns out to be, what 653 times 2 pi, and then divide that by 60 seconds. Well, the numerator part, the 653 times 2 pi, turns out to be 4,102.9. And that's radians. And then my denominator is 60 seconds, so all I have to do is divide that by 60, and that'll tell me per 1 second. And that turns out to be approximately 68.4 radians per second. Well, I've got my radius. It's 0.325. And I've got my radians, and that's about 68.4. And if I multiply those, I get approximately 22.22. So they wanted it to the nearest meter, right? Nearest meter. And so that's 22 meters approximately. So that's the answer to our question. How far does the car travel in 1 second? It travels 22 meters per 1 second. Well, that's going to do it for our lesson today. So come to class ready with all of your questions, and I'll see you then.